My name is Konstantin, and you're watching the Introduction to LLVM Intermediate Representation Programming Language for Beginners. The first topic that we're going to cover is the difference between pass by R value versus pass by pointer in LLVM programming language. So in the C programming language, there are two ways to pass data into a function. First one is pass by R value. So pass what we normally think of pass by value is actually pass by R value. So just the value is passed in without having an identifiable memory location. The parameter and the argument that is passed in are different entities, so a copy is created. And in pass by pointer, an L value is passed in, having an identifiable memory location. The parameter is a pointer to the memory location of the argument. It is allowing us to modify the data at that memory location. So here I am having two functions to demonstrate this concept. The first function demonstrates pass by pointer. The second function demonstrates pass by R value. Now in the main function I am allocating a 32-bit integer and assigning the value 5 into it. And I'm calling pass by pointer here with that variable. So %var is a pointer to 32-bit integer. So the actual pointer to the allocated stack memory is passed in, and a store is performed into that memory location, as you see here. This works for variables in the memory only. Allocated stack memory or global variables. It does not work with virtual register variables because they do not have an identifiable memory location. So you cannot change them indirectly. Now, after that, I'm calling pass by R value function. This one only works with virtual register variables. So if you want to pass a variable in the memory by R value, you have to manually perform an L value to R value conversion by first loading that value into a virtual register variable and then passing that virtual register variable into the function. We can assign a new value, but we can't modify the original value, and we don't even have access to the memory location in the function anymore, since we passed a value and not a pointer in. So there's no way to change the original value, this var right here. So, and if we assemble the LLVM intermediate representation code into a bit code and run it through LLI, the LLVM interpreter, and then we echo $? That prints us whatever the main function returned. So what does it return? We load whatever has been the most current value stored into %var, and then we return it, and we see it is 8. Why is it 8? We stored a 5 into it. Well, when pass by pointer called, it successfully indirectly stored a new value into the original variable because we passed it by pointer. However, we could not pass it by R value. and because it's returned an 8, we can make sure that this code works. Now, the important thing to take away is that whenever you want to do pass by R value, you have to manually perform L value into R value conversion, which is normally done through automatically by the C programming language. More examples of implicit conversions on the next slide. Now we're going to talk about some other implicit conversions. Namely, in LLVM intermediate representation, there are no implicit conversions. High-level languages might get away with implicit conversions, but LLVM intermediate representation, being a portable assembly language, all implicit conversions are exposed, and they have to be explicit now. An example of this is truncation. So truncation is performed implicitly. In the C, whenever you assign a number with a larger bit width into a smaller bit width. In LLVM IR, you have to do it manually. With the trunc instruction, the trunc instruction truncates a larger bit width into a smaller bit width. It just chops off the higher order bits that don't fit. In this example, in the C code, I'm having a 32-bit integer I here, and then I'm assigning it into a 16-bit integer S here. Here we can see the complete binary representation of both of these integers. We see the individual ones and zeros, and these extended zeros right here are just a shorthand way of saying that all of these other bit positions are all zeros. They're all zeros. So I didn't feel like writing out all the zeros, so we can know that all of these bit positions are unset. So which bit positions are set in this integer I? The 2 to the 23rd power, the 2 to the 21st power bit, the 2 to the 14th bit, and then these 3 bits here, which represent the 7. So if we evaluate this expression, what are all of these bits added together? It is this number, this big number right here. So we store it into the I, and then we perform a truncation from the 32-bit integer I into a 16-bit representation, which chops off all of these higher order bits. And then we print the unsigned 32-bit integer. That was the same value that we assigned it. But when we print the unsigned and signed versions of the 16-bit integer, it is 16,391, which is 2 to the 14th power plus 7. So since the signed bit here is not set, the unsigned and signed representations of the 16-bit integer are the same. Here we have a second example. You may be wondering, what if it was not this bit, but what if the signed bit actually happened to be set in the 16-bit integer after you performed the truncation? So let's go through in this example. The 2 to the 23rd, 2 to the 21st power, 2 to the 15th power, and 7. All of these bits are set in the integer I, so we assign that number, and then we truncate I to 16 bits, assigning the result into S, 16 bits. And then we print what is the 32-bit integer and we print both the unsigned and signed versions of this resulting 16 bits. So since the signed bit is set this time, upon truncation, the signed representation of the 16-bit integer is different than its unsigned representation. Integer data types in LLVM IR are not inherently signed or unsigned. How the bits inside the destination variable are interpreted depends on the application code. For example, you can print the variable as either signed or unsigned. There are separate arithmetic instructions also for signed and unsigned. So here, if we take the signed representation of this bit pattern, it's a negative number, and if we add 2 into 2 to the 15th power to it, we get the positive, we get the signed value out. Now, why is that? It's because this bit right here represents a positive or negative contribution of 2 to the 15th power. It is positive 2 to the 15th power when unsigned and negative 2 to the 15th when signed. So the difference between these two numbers right here is 2 into 2 to the 15th power. So using this formula, we can convert, and indeed we see that we get the same number as the unsigned representation of the bits when we add it to the signed representation of the bits. So we add 2 to the 15th once to get rid of the negative, and we add it twice to make it a positive. Now let's go for our third example. Here we are performing a truncation from a 16-bit integer into an 8-bit integer. And here we have some, this bit set in the higher order bits. And this number happens to be 544 that we're assigning to the original 16-bit value. So the point here is that truncation can lead to lost data if the value does not fit into the smaller bit width, because there's nowhere for these higher order bits to go when the bit width is reduced to 8 bits only. So truncation actually happens very mathematically predictably. The result is C, which is the value of the 16-bit integer, mod by 2 to the 8th power. So 2 to the 8th power is this bit position right here. And if you think about it, all the other, anything greater than or equal to 2 to the 8th power is evenly divisible by 2 to the 8th power, therefore its modulo value is 0. However, anything less than 2 to the 8th power does not go evenly into 2 to the 8th power, therefore ends up as a remainder. So it just retains its own value. That is why this formula works upon truncation. If we apply this formula, we see that 544 mod by 2 to the 8th power is indeed 32, which is also the value that we get experimentally when we try to print the unsigned representation of this 8-bit number. So we might conclude that to prevent losing data in this way, we should not have any bits in the higher order half. But this isn't necessarily true. There are some circumstances under which we can perform truncation, having bits in the higher order half and also preserve our data value. That's what we're going to talk about next. This is an example of that. So here we have a negative number, -4, and we see that this number has bits in the higher order half, and then we assign it into a 16-bit number by performing truncation. So there are some values, such as negative numbers, which can have bits in the high order half and be successfully represented in smaller bit width upon truncation. In order for that property to hold, the negative number must be greater than or equal to negative 2 to the power k minus 1 if the number is truncated into k bits. So -4 can be truncated into up to k equals 3 bits and maintain its same value, because this bit right here represents a contribution of 2 to the -4th power in a negative number. So when we print the original 16-bit number, we see it is 65,532 as an unsigned representation, but if we consider it as a signed representation, it is -4. Similarly, if we print the resulting 8-bit value as an unsigned representation, we see that it is 252. The unsigned representation is different. Then it is a smaller number than the original 16-bit value. But since we're interested in the signed representation only, the value, the number here, is the same. It is -4. So if we choose to interpret this as an unsigned integer, then we have data loss. However, if we choose to interpret it as a negative signed integer, then we have preservation of data. So as you can see here, it is a matter of how the bits are interpreted, how you encode your data values in the bits. If you want to interpret the bits as unsigned, you are losing data. However, if you want to interpret the bits as signed, then you are not losing data. Now, next kind of implicit conversions are sign extension and zero extensions. Sext versus zext. Here we are having a -1 and we are assigning it to an int s. So in the C programming language, we are performing sign extension. So sext basically extends or duplicates the signed bit, the most significant bit of the low order bits, into the higher order bits of the destination variable, as you see here. This is this example on the right. We assign a -1 to this s variable, and when we do a sext from the 16 bits into the 32 bits. If we print the unsigned version of the 32-bit resulting to 32-bit integer, we see that it is indeed a larger number, but since we're only interested into the signed versions, we see that indeed, because of the sign extensions, we have all ones and the -1 value is preserved. However, unlike sext, zext on the other hand fills the high order bits with 0 anytime, not depending if the signed bit is set or not. So in this example, we are zero extending the 16-bit number into the 32-bit number, which would basically involve putting zeros over the higher order bits. And if we print the unsigned representation of the original 16-bit number, it's 65,535. If we print it as a negative number, it's -1. However, if we print both the unsigned and the signed representations of the resultant 32-bit number, they are both 65,535, which means that basically all these lower order bits were copied in, and then the higher order bits were all filled with zeros. And the signed value is actually a positive number because the signed bit is right here in the 32-bit integer, not right here. So all of these numbers are treated as positive values. Next, conversion instructions that happen automatically in C are the bitcast instructions. So bits can be used to stand for any data representation. The bits themselves are meaningless without an interpretation. Bitcast instruction reinterprets the bit representation into another data type, but it does not change any of the bits. So here, in this example, we're assigning 2.75 into a floating point variable. And this is the bit pattern for floating point value 2.75. Let us briefly see how it is being represented here. So here we have the exponent field. This bit right here represents a contribution of 128. So in order to calculate the final exponent, we do 2 to the 128, which is whatever value is encoded in the exponent field, minus 127. Now, where does 127 come from? So 127, the bias is actually defined for 32-bit floating point values, and it's defined as 2 to the 8 minus 1 power minus 1 for an 8 bits exponent. So that's that. And then in the mantissa, this set bit right here represents 1/4. This bit right here represents 1/8. So if we add 1/4 and 1/8, we get 0.375. However, this number is actually 1.375. Where did this one come from? Well, the implied 1 in front of the number is also defined according to the IEEE floating point standard. It is added onto the mantissa by the floating point unit hardware. So it is part of the algorithm that interprets these bits into a floating point number. And if we evaluate this expression, it's basically 2 to the first power times 1.375, which indeed equals 2.75, which was the number that we assigned here. So now when we do a bitcast from the float into the 32-bit integer, none of the bits change. We just reinterpreting them as an integer data type. So this bit is set, this bit, and this bit is set. So this bit represents 2 to the 30th power. This bit is 2 to the 21st power, and this bit is 2 to the 20th power. And if we add these numbers together, we see that it is 1,076,887,552. So we want to make sure that the program works as we think of it in theory. So after the bitcast, print the float value, it's 2.75, and we print the unsigned 32-bit version of this same bit representation, and indeed it is this same very large number. Now going in the other direction, a bit cast from int to float. I know the bit pattern for any arbitrary floating point number, so I can write the encoding as an integer and convert that to a float using bit casts. Now, suppose we want to represent infinity in a floating point format. What would it take? Well, infinity in a floating point format is where the entire exponent field is all ones and all the other bits, the rest of the bits are zeros. So this whole mantissa field is zeroed out. That is what this stretched out zero means. It's just a zero initializer. So these set bits in the exponent actually representing powers of 2 from 2 to the 23rd power to the 24th all the way up to and including 2 to the 30th power. These bits make up the entire exponent field. So what would be this value represented here in this integer? Well, we just add all of these contributions of these from 2 to the 23rd to 2 to the 30th power. So here I'm having just a simple Python script that would add up all the powers for me, and in the end we get 2,139,095,040. So we are assigning this value into the I, and then we do a bit cast from the 32-bit integer into a float, and that works because a float is also 32 bits, so any bits that are in the 32-bit integer can fit into a float. And then we print the original 32-bit integer, we get that same large number, and when we print the float, we indeed see that it is infinity. So our experiment has worked. Now the next topic that I would like to go over is instruction composition. Yeah, so this is familiar. In the C programming language, we can write complex, arbitrary arithmetic expressions on one line. Although we don't think about it, each expression takes multiple steps. These steps are very apparent in the regular form of the program, where each step gets assigned its own virtual register. So first we add these two numbers together, and we add these two numbers together, and then finally we multiply the results of these two sums. So the takeaway point here is that since each primitive instruction is also a typed single static assignment value, nothing stops us from composing an expression made up of operations performed on multiple single static assignment values. An instruction expects values of certain types. For example, this multiplication instruction expects two 32-bit operands that it multiplies together. So we can insert the returned values of other instructions, and then as well we can insert these two add instructions in as the operands into the multiplication instruction, since the multiplication instruction expects two 32-bit integer values, and both of these two add instructions, when they add these two numbers up, they also return 32-bit integer values, which is the correct data type for the operand of the multiplication instruction. So this just works, and it is equivalent to this line right here. So we use instruction composition to combine long lists of instructions into expressions, which may be potentially more readable and take up less lines of code. if we have long lists of instructions and each instruction is a single static assignment value, it is also a virtual register. So we end up with many virtual registers for storing the intermediate values. And we can have less virtual registers by combining temporary instructions into one big long expression. If a virtual register is only used for storing an intermediate value in a calculation and it has only one user, it is only used in one place by one instruction, and after that it is never accessed again anywhere else in the code, then we shouldn't be keeping that virtual register around. If the value of that virtual register is not used in multiple places, such as a common sub-expression, it could be effectively removed and the instruction just put into one big expression in line. Now we're going to look at how we can do dynamic memory allocation and the LLVM intermediate representation code. So LLVM IR does not natively support dynamic memory allocations, although in previous versions there was a dedicated malloc instruction, but nowadays you basically just use the C API. So we would use malloc 3 as we would in C code. So we first open the man page, man malloc, to find the signature of these two functions, because we have to provide an equivalent declaration in order for these functions to be linked into the completed executable. So we see the signatures here, and now we have to figure out what these data types are. Now size underscore t is 8 bytes, and 8 times 8 equals 64 bits. So it is a 64-bit integer. And since LLVM IR does not care about signed or unsigned, we only care about the size of the data type, and it is used for both signed and unsigned values. And here we're also having a void pointer being returned by malloc, and the void pointer is taken in as a parameter by free. So in C we would use a void pointer as a generic pointer to any data type element. However, this is actually a quote from the LLVM language reference, which says, note that LLVM does not permit pointers to void, nor does it permit pointers to labels. Use I8 pointer instead. So we do that here. And after providing the equivalent declarations, we first need to define the size of an element that we want to allocate, which is 4 bytes, because we want to allocate 3 32-bit integers, and each one of those elements is 4 bytes. And then we multiply the size of each element by 3, and we get 12 as the total number of bytes that we want to allocate. And then we pass in the size of the allocation that we want, and we get a pointer out, and then we just return. So notice that I am not actually freeing the pointer anywhere, because I want to test whether or not the malloc worked by deliberately creating a memory leak. Now we take this memory leak LLVM code and assemble it into a bit code, then use the client compiler to compile the bit code into a machine specific architecture dependent assembly code. And then we compile the file into a .out runnable executable instead of running it with LLI, the LLVM interpreter, because LLI might introduce its own memory leaks or false positives. Because when you run your application with LLI, it is actually an interpreter or just-in-time compiler. It is another executable program that is running in addition to your own code. So it might also have its own memory leaks, and to eliminate that possibility, we want to make sure that the memory leak is indeed caused by our program. So we just run it as a standalone executable. So we run valgrind on that executable so that we actually see the memory leak. And when running valgrind, we need to use this // syntax if the executable is in a local directory. We do not use the // only if the executable is located in / bin or in any of the directories specified in the path system variable. And we run valgrind, we get this output, and highlighted here is our key line. It says definitely lost 12 bytes in 1 block. So we want to hold enough space to hold 3 4-byte integers. So that's where the 12 bytes comes from. And then 1 block means 1 malloc or 1 contiguous memory allocation. So since valgrind reports a memory leak, it means that allocating dynamic memory actually worked. And just to be super extra sure, if we go into the assembly code, .s file that was generated in the second command, we see that indeed malloc is getting called on the highlighted line. Now, an interesting thing that I noticed is that it's actually performed an optimization for us by moving 12 into EDI, which is the register holding the argument to the function. I find it interesting that the LLC compiler actually performed an optimization, which is constant propagation. It saw that it could multiply these two integer constants and put the result into the assembly code versus having the executable do the multiplication by itself. So that is just an interesting optimization that it can do. Now we are going to look at get element pointer instruction, which is rather tricky to understand for beginners. So get element pointer instruction gets a pointer to the element offset by the base data type. It is particularly useful for accessing elements in arrays, but it can be used to arbitrarily index and access any memory location. So get element pointer can only be applied to pointers, memory locations. So only global variables are allocated stack variables. It cannot be applied to virtual registers because virtual registers do not have any memory locations. Now, in this code, we are having 4 global variables. And it is worth noting that global variables are stored one after another in memory. So we assign 5 into num1, we assign 6 into num2, 7 into num3, and 8 into num4. And we have all these variables packed as tightly together as possible. They're just one alongside another. So, and then we do a get element pointer on one of these variables. So we load the I8 data from the I8 pointer. We load the 8-bit integer from the memory location. Now, in order to do that, you first need to get a pointer to that memory location. So you do the get element pointer. And then after loading that value from whatever the pointing is pointing to, we do 0 extension, because the return type of main is an I32, so that's what this X is useful for. And we return I32 %1 because we don't know how to call printf yet, but we want to see what was the value that was accessed by the get element pointer. So it returns whether a number was accessed by the memory operation. One thing worth noting is that this get element pointer instruction does not do a dereference or memory access. It just computes the address. The memory access is done by the load on that address. And if we assemble this LLVM code into the bit code and we run the code using LLI, we echo $? We get the return status, which was the value that was accessed by the memory operation. Now, if you run this program as it is with this offset of 0, it basically says get a pointer to an I8 starting from the I8 pointer num1 offset by 0 I8 elements. So we get the 5, which makes sense because that is the address, that's whatever value was stored in num1, and we have an offset of 0 elements. Now, if we change this 0 to 1, we get a pointer to an I8 starting from the I8 pointer num1 with an offset of 1 I8 elements, and we get the 6. So it just happens to get the next variable stored in the adjacent memory location, which corresponds to num2. If we change the offset to 2 I8 elements from the starting address of num1, we go 1, 2, and it gets the 7, which is num3. And if you go to an offset of 3 elements away from the starting address of num1, we get the 8, which is num4. Now, so this is proof that the global variables are stored one after another in memory. Now, you might have a question, what if we put the 4 here just for fun? What if we go 1 past that? What would we get? Well, because we're now accessing memory that is beyond our control here, we could get just about anything. However, we get the 0 here. And we get 0 because it is a global variable. The entire global section is zeroed out at the start of the program. However, if it was a stack variable, we would get a different result. Now we're going to see analogous code in C programming language written using the exact same paradigm as the LLVM code. So once again, for global variables having the same assignments, and they are stored one after another in memory. Then we get the pointer to the element by starting with the address of num1 and performing an offset. We get the pointer, and then we dereference that pointer to get the value, and then we return the value. So if you run this code, the C code with different offsets, the output is exact same as in the previous LLVM intermediate representation code. So we want to understand what the LLVM IR code does. So similar to get element pointer, the first line just computes the pointer address. We first get a pointer to an element and then we dereference that pointer. Hence the reason for the name get element pointer. So the first line does not do the memory access. The second line really dereferences it. And another interesting thing in C is that we can just do plus pointer to offset onto the next variable in memory. So we can perform pointer arithmetic using this syntax, as well as explicitly adding an offset to the original pointer. Now you might be asking, what happens if we go too far? If we put a really large number as the offset? Well, would it work or not? It depends on what is your definition of work. If the program crashes, no, it doesn't work. If the program doesn't crash, well, then it works, but you might be overwriting memory that you do not own. So you might have a bug there because some variable was overwritten. Now going back to the LLVM intermediate representation code, you might be asking, what happens if we use local variables instead of global variables? Would that make a difference? So here we're allocating num1, num2, num3, and num4 as local variables on the stack. And then we store values into those variables. 5 into num1, 6 into num2, 7 into num3, and 8 into num4. However, the bottom part of the program is the same as before. We get an element pointer using an offset, load the value from the pointer, and return it. So let's run it. Using the offset of 0, we get 5, which is what we expected. It's just num1 we are accessing here. If we specify an offset of 1 i8 elements from the starting pointer num1, we get an 8, which is unexpected because we expected for 6 to be there, because 6 is the next variable that was allocated. But it returned us 8, which implies that it is num4 which is being stored here. That's strange. So now let us do an offset of 2 elements away. We get the 7. So that's a relief, because that is expected, because 7 is exactly 2 elements away from num1. So it is num3 which is stored here as expected. Now if we go 3 elements away, we get the 6, which is num2. But we expected it to be num4. So it seems that it swapped the memory location of the num2 and num4. So there is num4 instead of num2 and num2 instead of num4. That's interesting. And if we put the 4 here, we go one place away, we get a 14 out instead of a 0. Now, in the previous example, we got a 0 because it was a global variable. The entire globals section is 0 at the start. So, because alloca creates variables on the stack doesn't get zeroed out like the globals section. So we get a garbage value as the element at position 4. And the second conclusion or observation that we can make is that alloca can apparently rearrange the allocations on the stack to however it pleases as it rearranges the num2 and num4 variables. We don't know for sure exactly in what order the variables will get allocated on the stack. So from the LLVM language reference manual, it says the order in which memory is allocated, which way the stack grows, is not specified. So these may be in any order really for allocated variables. Okay, so now we're going to take, we have seen an example of using get element pointer with individual variables. Now we're going to see an example of get element pointer with arrays. So in C programming language, we can also use alloca, but it is a function, not an instruction. I'm just using it here to simulate the paradigm of LLVM intermediate representation in analogous C code so that we can get a better understanding of it. And we use it similar to malloc, providing the size of the data type as an argument, and it returns a pointer to that allocated data type. So if we allocate an int, we get an int pointer out, a pointer to that allocated integer. Now, because it's a pointer to int, we first get an offset from that pointer, and then we dereference to get the memory location. So here the offset is 0 ints from the original pointer, so it's just the same as dereferencing the original pointer. Yeah, so we first apply the offset, and then we do the dereference, regardless if the offset is 0 or if it's actually something meaningful. And then we get our actual memory location to which we can store a variable, a value. So this x plus 0 dereferenced is actually equivalent to x bracket 0. You might be thinking, is this array accessing syntax? Well, yes and no. The array accessing syntax isn't special. It's just an offset and a dereference from a base pointer. Actually, there is no array here. We just have a pointer to a single integer that we are applying the offset and dereference on. So this code is functionally equivalent to just dereferencing x, but this array syntax is really just a syntactical sugar for an offset and then a dereference. So here, for your reference, are 4 different equivalent types of addressing memory and dereferencing it in the C programming language, but we're not going to go over that now. Instead, we're going to look at an array example. So in the C programming language and LLVM IR as well, when you allocate a variable of that type, you get a pointer to that variable to that type. So when you allocate an int, you get an int pointer. When you allocate an array of 3 ints, you get a pointer to an array of 3 ints. And the size of int 3 is 12, so we are allocating 12 bytes here. So pointer arithmetic increments the pointer by the size of the pointy type, which is an array of 3 ints. So incrementing the pointer jumps it forward by the size of an array of 3 ints in memory, as we see here. When we apply an offset of 1, it actually jumps forward by 12 bytes, which is the size of an array of 3 ints in memory. Yeah. So the data type of this p plus 0 as well as the data type of p plus 1 is just a pointer to an array of 3 integers as is the original p. Now, the first index in LLVM IR that we see here, it just offsets the pointer. It does not dereference anything. So likewise in C, the data type stays the same in LLVM IR also. And because of this, the first index is always 0 because we want to stay where we are at. We don't want to jump forward in memory into some memory location that we don't even own. Now, when you dereference that pointer with the offset, which is a pointer to an array of 3 integers, we get the data type of whatever the pointer is pointing to. In this case, it is just an array of 3 integers, which is the same thing as a pointer to the first integer in that array. So it becomes an in pointer. So now performing pointer arithmetic on that moves you forward one array element in memory, as we see here in this example. When we dereferenced p plus 0, we got a pointer to this element, and plus 1, it jumps us to here. So the second element in LLVM intermediate representation that we see here, it actually does two things in one. It first dereferences a pointer to the array of 3 integers, getting us an int pointer, and then it adds the second offset onto it. So as we see in the diagram above, its offset is an int pointer. Now in C code, dereferencing that pointer creates an int L value, which is a memory location capable of receiving data that you can put into this box. So unlike in C, in LLVM intermediate representation, getElement pointer cannot dereference the final address to obtain that memory location. Instead, store must be explicitly used on that pointer to store a value into that memory location. The getElement pointer, it can dereference the outer pointers, but it pointers, but it cannot dereference the final pointer explicitly and store a value in. We have a specific instruction for that. Now let's look at an example of a two-dimensional array. In C code, you would usually create a two-dimensional array like this with 2 rows and 2 columns, and we assign 2 into 0, 0, 5 into 0, 1, 7 into 1, 0, and 9 into 1, 1. Now, we can rewrite this same code in a different version of C code, which is the C code written in the paradigm of LLVM intermediate representation, making use of alloc instruction. So we want to allocate a 2D array of integers, and we get a pointer to that type. In LLVM IR, we also get a pointer to a two-dimensional array. So allocating a two-dimensional array means allocating an array of 2 elements, where each element in that array is an array of 2 I32s each. So yellow here is the number of rows and green is the number of columns. And now, because we get a pointer to an array and not an array itself, we need to have the first offset here, which is always 0. And the next offset is for the rows, and the next offset is for the columns. And in LLVM intermediate representation, we first get a pointer to the array element, and then we store a value into that memory location. So this p.0.0 and p.0.1 is just a name. You can name it to whatever you want, but since LLVM does not have the dot operator, we can use it as a valid character in our variable names. Now, in the last example of implicit conversions in LLVM intermediate representation that I want to demonstrate is pointer to int and int to pointer. These instructions basically do what they say. In this example, using the code from the previous slide, we want to perform a manual address computation, which is what the processor does when it computes an address. So here we are having a diagram of that same two-dimensional arrays, but drawn in row major order, meaning first we have the elements of the first row laid out, and the elements of the second row are laid out directly after them. So this p pointer is pointing to the starting byte of this whole entire array. So first we get a pointer to an integer. We convert that pointer p into a 64-bit number, because on 64-bit operating systems the size of a pointer is 64 bits, and on 32-bit operating system the size of a pointer is 32 bits. So if you're on a 32-bit system, you should change this to I32 instead. Then we calculate the size of a row in the matrix, which is the size of an element 4 bytes times 2. So there are two 32-bit integers in a row. And then we multiply the size of a row by the number of rows to offset, which is the first index offset. And then we multiply the size of an element by the number of elements or columns to offset, which is the second index offset. And then we add the rows offset and the columns offset together to get the final offset from the base address. And then we add the offset to the array address, obtaining as the final address. It's still an integer though, so we need to convert it into a pointer in order to be able to load from that memory location. So that's what the int to pointer does. It just converts that address represented as 64-bit number into an I32 pointer, element pointer, which is pointing to right here. So then the 7 is loaded from the virtual register and returned. And if you get what that return element value is, you would indeed see that it is a 7, and the manual address computation was successful. So that's an example of pointer to int and int to pointer. What are they used for? Now, here is an example of rewriting that same code using instruction composition. And we can do it since there are just a bunch of sequentially executing arithmetic instructions which never get used again. So this is the equivalent code using instruction composition. In order to understand it, we read it from the inside out. We basically multiply 4 by 2. That is the number. That is the size of a row multiplied by 1. That to get the offset of rows, how many rows we want to offset, and then we multiply the 4 by the 0, which is the columns offset, and then we add the rows offset and the columns offset to get the final offset, and we add the final offset to the array address to get the final element address. So it's more lines, but it is potentially easier to read than the example on the left, mainly because I specifically structured it in a hierarchy in order to be more readable. And we also save registers. Instead of having all of these virtual registers, we only have one virtual register. And that makes sense because we want to use as few virtual registers as possible. Otherwise, we might have inefficiencies such as we run out of registers, which makes register allocation algorithms, it could make them more complicated. So we're helping the compiler. Now let's take a look at a possible error that could occur when you're using getElementPointer on an array. Here we are allocating a global array of 4 32-bit integers and initializing them all to zeros. And then directly after that, we're allocating a global variable. It's just an integer and assigning it with the value 8. So the number is directly in the array, in the memory after the array, or rather their memories are, since this at number and at array are actually just pointers to the allocated memory locations. So I'm using I64 as the index inside this getElementPointer since the size of size_t is 8. So we're doing a getElementPointer on this array, and suppose that instead of having the first index, the first offset being 0, we have it being 1. And because this at array is a pointer to an array of 4 elements of 32-bit integers each, when we do the offset of 1, it actually takes us to this non-existent array of 4 integers in memory. And then the second offset is 0, which takes us to the first element of this fictitious array, which just by chance happens to be the number. And then we store a 9 into whatever that pointing is pointing to, overwriting the previous value that the number had. So now we want to test what the number value is. We load that value from the number. we expect to be getting an 8 because if we view all the lines above, nowhere did we do a store into the at number variable. We just did a store into this array, so it should be safe, right? Well, no, because we made an error and we modified adjacent memory locations that we should have never touched. So in order to prove that actually happens, we're loading that number variable, and it's an int value 9. However, I want to print it to the screen. So I call putchar, and in order to convert it from an integer, the 9, from an integer representation to a character representation, I add 48 to it, which gives us the character representation. So 9 plus 48 is equal to 57, which is the ASCII value for the character 9 on the keyboard. So that is what will be printed here in this line. And then we're printing the ASCII value 10, which is the new line character. So we want it to be 8. We want 8 to be printed, but not the value 9 is actually printed because the value of the global variable is modified through the inadvertent memory access. So it's trouble. Now I'm going to demonstrate a practical example of working with get element pointer and arrays in LLVM intermediate representation code. Here we are allocating the an array. It's the same global array with 4 elements in it, initialized to zeros, and now we are putting the size of array as a global variable in front of the actual array, so that we don't have a off by 1 error and accidentally overwriting the array size. So this is an example of looping an array and filling all its elements. The array is initialized with all zeros, but we want to set custom values in the elements. So this is a common operation that you would usually do in C code, and we have to know this for LLVM. So this counter init is a 64-bit integer because size underscore t, which is commonly used for indexes and sizes, is 8 bytes long. So it's a regular for loop. In the for condition, we are getting the counter value being the initial counter value, which is 0 if we came from the initialization basic block, or we get whatever is the new value of the counter, the updated one, if we come from the body of the loop. Then we get whatever is the size of the array, and we compare the value of the counter to the size of the array. And if it's less than the size of the array, then we go into the body of the loop. And if it's not less than, then we reach the end of the loop. So we just go to the end of the loop. We break the loop. And now in the for body, we do a get element pointer, and the most important thing is that get element pointer can have a variable as an argument, as an offset. So we're using the counter value to obtain an offset into this array and assign each array element with a corresponding value. So this counter val was defined in this for condition, which necessarily precedes this line here. So into each memory location, we are assigning this value, which is just 1 plus the counter value. So each element in the array gets a value which is 1 greater than its index. So we have this. And at the end of the loop, all the elements are printed, and we're calling this function, passing a pointer to that array into the C code, and it basically just loops to the entire array in C and prints every number using printf. And if you would do that, you would see that it is indeed 1, 2, 3, 4. Now let's take a look about structs in memory and how we would access them. So when accessing fields of structs, LLVM intermediate representation has no concept of padding or internal alignment. This is an OS specific thing. For example, padding and alignment of structures is different in 32-bit Windows and 64-bit Windows, as well as in Linux. So even if your structures have the same elements in them, the size of and the layout of those elements in the memory depends on whatever operating system you're running, and they might be different depending on the operating system. But LLVM intermediate representation has to be cross-platform compatible. That's why it doesn't care about padding and alignment. So a struct is actually just a bunch of variables of potentially different data types offset a certain number of bytes each from the starting address of the struct. That is how we think of a struct in low-level code. Both get element pointer as well as instructions operating on structs in virtual registers, which are used for accessing data inside of structs, automatically calculate the offsets of different fields in the struct, which means that programmers who write code in LLVM intermediate representation language do not have to worry about padding and alignment. When accessing fields of structures, we use a higher level syntax. These are definitions of struct types in LLVM IR. It's basically the same thing as struct declarations in C code. However, with the additional thing that basically fields of structures in LLVM IR are numbered like elements in arrays starting from 0. They are unnamed. So this is field 0, field 1, field 2, and so on. So they don't have names. We just specify the data type of whatever element that is. And we can have elements of different types in a struct. And we can also have other struct data types inside of a struct. For example, this vertex type consists of a color and a position and just a plain 32-bit integer. So an interesting thing that I noticed is that even though the definitions of struct types reside in the global scope, their names start with a %, just like local names. If we enforcingly put an @ sign instead of the %, we would get an error here. It says expected global or constant. The @ sign and % are basically just arbitrary, but just to remember that for structure types, we use the %. That's just something you have to memorize. So it's an exception to the rule of having @ symbol in global names and % symbol in local names. Yeah. So how we access field of these structures depends on where these objects are located. For objects located in memory, get element pointer is used to get the address of the desired field. And then we use load and store on it just like any other variable in the memory. There really is no difference. Now for objects located in virtual registers, as we will see shortly, since such objects don't have an address in memory, get element pointer cannot be used. Remember, they are R values. They can't be modified. However, we use the instructions insert value and extract value for getting values out of objects stored in virtual registers. Struct objects in the virtual registers respect the single static assignment property. Modifying the fields of structure objects residing in virtual memory registers can only be done during the initialization. We are using specialized instructions for that. The actual virtual register variable cannot be reassigned to something else, and it should not be reassigned if we want to keep the exact same instance of the structure object. Now, here we're first doing a get element pointer example. So we're having a vertex pointer here, and since the v1 and v2 are allocated vertex objects, they are both pointers to the vertex structure type. So the first offset performs pointer arithmetic on the pointer to the actual structure type, just like in the array examples shown previously. The next offsets are used for indexing into the nested structs, and there may be more than one onion level, and getting a pointer to the desired field. And after that, we store into that pointer just like any other variable. So here, this first offset doesn't do anything. The second offset, it goes to the field number 1 of this vertex, which is the position struct. And the second field, second offset, it goes to the 0th field of the position structure, which is inside of the vertex structure. So we get this pointer to this field I've named X. It is not a name, it is a comment since the fields are numbered, but this is just for clarity. So this is a pointer to the X variable in the position, which is inside the vertex, inside the V1. And then here, for the second memory access, where the 0th this index doesn't do anything, and this gets a pointer to the element at index 2 at this field 0, field 1, field 2. So it gets a pointer to this i32 integer here. So this v1.position.x and v1.i32 are just names. They could be anything really. And then we load, and after doing the store, we load the value from this field and we load the value from the other field, and we add them to and return the result. And if you would look at the return value, you would see that it is 15, which means that these two stores and their corresponding get element pointers were successful. And finally, to wrap up this lecture, we're going to look at the structs in virtual registers, how they are stored. So we use insert value instruction to create struct in a virtual register. It takes a struct value to use as a base. So first is the data type of the struct, and then we have the value, which can either be a structure constant, as we see here, defining the initial values of all the fields in the struct, or instead of this, we can have an already existing struct object residing in another virtual register that we can use as a base for this struct. And then it takes a value to write to a particular field in the struct with its offset. So for example, here we are creating a struct with two 32-bit integers initialized with 4 and 8, and then we are into that struct here, we are inserting the value i32.1 into the 0th field, which overrides the 4. And then we do extract value, which takes an object, a struct object, which is the data type of the struct and the variable, and we want to extract the 0th field, and then we return that value, and we see that it is indeed 1. And if we want to get the field at index 1 in the struct, we get the 8. Now in this example, we are initializing a struct with two variables, 4 and 8. However, this time we are inserting the i32.1 into the 1th element, which overrides this 8 right here. So if we get the field at offset 0, we get the 4. And if we want to extract the field at offset 1 from this object, we are getting the 1 out. So an interesting thing to notice is that after doing this insert value, we cannot do an insert value on this object again, since that would be breaking the single static assignment property. We can only do the insert value once. So we are inserting a value at a specified field into a struct, and we could also have a different object here instead of a structure constant, which would basically create a copy of that original object and insert the value i32.1 and then assign it to the new variable, leaving the old variable unmodified. So that's it for now.